Hey yo, welcome to Astronaut. Today we're going to break down white dwarfs. White dwarfs are often placed into this broader terminology of stellar remnants, compact objects, dead stars, etc. But some of those phrases are a bit misleading. Let's get into it.
I feel like an astronaut in what you know about rolling down in the deep.
There's this image of an HR diagram at the Griffith Observatory in LA, California, that says white dwarfs make up 3% of all stars. And while I'm all for the Griffith Observatory making astronomy more accessible to the public, that phrase doesn't really make sense. Because white dwarfs aren't stars, although they are related to stars. A star is an object that can sustain itself through nuclear fusion. The pressure it exudes outward due to this fusion is in balance with the gravitational pressure pushing inward. Eventually, though, that fusion will stop. The sun, for example, is fusing hydrogen into helium, but once it runs out of enough hydrogen to fuse, the gravitational pressure acting on it will be stronger than the pressure it is able to generate. At this point, the star will start to collapse. But wait, as the star collapses inward, it's going to heat up. This allows the star to once again fuse the thin shell of hydrogen in its outer layers. The extra heat causes it to swell up, several times larger than the initial size of the star. Although the core is extremely hot, this increased volume causes the surface of the star to cool, which in turn causes it to become increasingly red. It is now a red giant. In the hot core, the star will now start to fuse helium into heavier elements like carbon and oxygen. For a star the size of the sun, the core won't be hot enough to fuse any other element, so the core will contract again. As the core contracts, it releases energy that causes the star's envelope to bloat up even more and ionizes expelled gas. This glowing gas is what is known as a planetary nebula. Now, the star is unstable. It will blow away its outer layers, leaving behind just the carbon-oxygen core. This leftover core, which is about the size of the Earth, is called a white dwarf. The remnant is no longer fusing, so it is retired from being a star. However, initially it will still glow. Over time, the white dwarf will cool and lose its luminosity, eventually turning into a black dwarf. Black dwarfs are still just a theoretical concept because it's incredibly challenging to observe an object that has no light and little gravitational pull. Not to mention it would take billions of years to cool, and the universe isn't old enough for a star to have lived, died, cooled, and gotten to this point. Astronomers sometimes measure the luminosity of white dwarfs to backtrack how long ago star formation began in a particular region. This process is the future of main sequence stars, 0.8 to 8 times the mass of the Sun. At the end of their lives, the smallest stars become giants, dispose of some material, and the compact cores left behind are called white dwarfs, which fade and cool off over billions of years. Let me draw this full process out just so you can see what the white dwarf formation looks like on an HR diagram. And if you're unfamiliar with the term HR or think it stands for human resources, I'll link a video in the upper right-hand corner of this one. We start with a smallish star, again 0.8 to 8 times the Sun's mass, on the main sequence. Once the star starts fusing helium, it veers off the main sequence and turns into a red giant. When it runs out of helium to burn, the star contracts and bloats up again, veering onto a track we call the asymptotic giant branch, or AGB for short. At this point, the star's core is primarily carbon and oxygen. These giants eject gas, and once the gas is ionized, a planetary nebula is formed. In the white dwarf phase, the leftover core will be much dimmer than before, so white dwarfs fall into the bottom left-hand corner of our diagram. Initially, the white dwarf still has a lot of heat trapped inside, but once it starts cooling to a theoretical black dwarf, it loses its heat and luminosity, meaning it will gradually move farther and farther to the right of our diagram. Well, that's all for now. Thanks for watching, and as always, ponder, wander, and go right in the stars.
Slow motion, yeah.